Let us start by reviewing what we've done so far with waves. So we talked about waves propagating out from point sources. So here we have 3 point sources and their waves are radiating out. And we said that at each point in the field out here, for example out here at this observation point, it's an oscillation. Where this term, the phase, has to do with when it's going up and down. So each point in here is going up and down at different times, so this accounts for that. Now, we said that if only one of these sources was going, you would have a different wave. So let's just say this one here is source 1. That's 2, and that's 3. So then you would have a different amplitude and a different phase. But they're all oscillating with the same frequencies, so that stays the same. So there's 3 parts to it. You have the amplitude, the phase, and then the time-dependent part. Okay, so any place in this field, if we took another point over here, it would have the same sort of thing. It'd oscillate up and down. Of course, the phase would change, and the amplitude could change. So any place in this field, you'll have an amplitude and a phase. And you'd have a different amplitude and phase depending on which source is selected. Okay, so if we have all of them on, we get this one. If we just have source 1 on, we get that one. Source 2 on, we get that one. Source 3, we get that one. Okay, so this would all be at one particular point. Now, the superposition theorem tells us that if we turn on all 3, you get this, and it should be equal to the sum of what you got if you turn them on one at a time. Okay, so that's the principle of superposition. Okay, so just I want to review slightly this phase idea to make sure we're okay with it. So if you follow these red dots, they're moving up and down. So that's one point on the wave. And you can see that they're not going up and down in synchronous with each other. Okay, well actually some of them are. This one and that one move up and down together. Okay, but other ones are not. So we represent where we are in the cycle by an angle from 0 to 2 pi. Okay, so if we picked a reference point here in the middle as what we'll call 0 phase, as we move away from it, we build up phase here. You get the phase by using the distance you move. So in this case, 2 units. The wavelength here is 3. So if we calculate the phase at that point, we get the wave number times the distance traveled. And then this particular one is 2 units. So we get 4 pi over 3. So that's how you calculate this one. Okay, so the phase has to do with where you are. So in this particular case, it's computed by just taking the wave number times the distance from what you're calling 0 phase. The choice of where your 0 phase is somewhat arbitrary, so I picked this point to be phase 0. So after doing that, we looked at some patterns that emerged. Okay, so the first one was just a sequence of points in a row. So a row of point sources. They had a length A altogether. In this case, I've done the case where that length of point sources is 5 times the wavelength. And then we looked at far away from that slit, as we call it, and we looked at how the amplitude of the waves, or the intensity, the square of the amplitude of the waves, and we saw that they ended up having these simple patterns. If we go back to this thing, it doesn't look so simple, but you can see that it's already, even in a complicated situation like that, you get these sort of like lines building up, where there's high intensity, and other lines where it's low. Okay, so this is a particularly simple one, and there's actually a formula for it, which we gave a quick derivation of. Okay, so if we measure color, out here someplace, this is the angle theta, so the angle from the center. Okay, and so we find that if you go along on a given radius, you get a pattern sort of like this guy here. Okay, so that's how the intensity varies as you go around that circle. We also looked at double slit. This has that same single slit pattern because a double slit is made of 2 single slits. But on top of it, there's an extra oscillating pattern. So in this diagram, you can see that you have this overall envelope, which is the single slit pattern, but that gives the amplitude of the oscillation of this single slit pattern. Now our goal is actually for today, as I said, that we would see better where this comes from and understand it better. So that's the goal for today. And the double slit is a class of problems which are all very similar. So these are all, in some ways, the same problem. So in each of these, we have a source, a round thing, and an observation point. And then we have 2 ways to get from the source to the observation point. Okay, so here's one. There's a direct path here and a reflection. So maybe this is your computer, this is your Wi-Fi router, and this is your refrigerator. Okay, so here's another one down here. You have a path that bounces off of here over there, another one that goes like that, and there's a tree in the middle, so there's no direct path. This is another one, the one that describes this colored patterns on when you have oil on the surface of water. So there's the light that bounces off the surface between the top of the oil and the air, but there's another reflection off of the top of the water, so the interface between the oil and the water. Okay, so all of these have that same effect. And you can see that in the end, what we have is that It's sort of like having 2 point sources. There's two waves that come together at the observation point. Okay. So then we have sort of the same thing. If we just have one path, the first path, then we have some electric field at this point here. If we have just the other path, then we have a different electric field. And if we have both, we have a third one. And the principle of superposition says that those first two have to add up to give the third one. Now, after a little bit of trigonometry, I'll put a document on the web page that does this step. It's nothing that you wouldn't possibly have done in high school. You can show that this amplitude term squared can be computed from these amplitudes and the difference in these phases. Okay, and this is the formula. This is probably the formula of the day. Okay, so this works anytime you have two ways of getting from the source to the observation point. Okay, and all you need to know is think about what all these terms are now. You have the phases, and those come from here. Okay, so if you just had one of the paths open, this would be the phase of that wave at the observation point. If you had the other path, this would be the phase. Okay, then the other thing that's in here is just these two amplitudes. And again, those are the two amplitudes with each path individually. And then this guy is the amplitude when they're both open. Okay, so it's a nice equation. This actually comes, if you remember the law of cosines, this is a form of the law of cosines. All right, so I graphed this. And so you can see that what I've graphed is how does this amplitude change when as the phase difference changes. Okay, so you can see that this is a constant, another constant times the cosine. So it's not too surprising that it looks like a cosine graph. So the peak is at 0, first minimum was at pi, so it's just that cosine graph bouncing up and down. The minimum value is when the cosine is -1. And in that case, I hope you can see that if the cosine is -1, then we have these two terms minus that term. And that's actually a perfect square. That's this. I've dropped the little zeros on these guys because they just didn't fit. All right, whereas the maximum occurs when the cosine is 1, and then you have these two terms plus that, which is E1 plus E2 squared. So the oscillation goes between those two extremes. Okay, so we have some special cases. This is the maximums. And if you look, where do the maximums occur? It's every time this 2 pi is an even the phase difference is an even multiple of 2 pi. So when n is even, it's a max. And the minimums occur when n is odd. So it's a nice result. All right. right, so this works for all of those cases that we pictured up here and any other one where the light can arrive by two paths. But now we want to go and see if we can't find how we got this equation for the double slit. So let's look at the geometry of the double slit, and that will help us find that equation. So in the double slit, I've drawn them here so that the slits are very, very small so that you can see the scale of the observation point. But because they're so small, you can't really see the slits. Now in this case, we know that each slit is just a single slit. So we should have this single slit intensity pattern on this screen. So there'll be the big peak in the middle and the side lobes out there. Okay, so depending on the angle, we'll get more or less intensity when just one slit is open. If the other slit is open, presuming that they're same, you'll actually get the same intensity. So the two intensities are the same in this case for the two slits. This allows for some simplification. So let's remember the formula that we got for the total intensity. Did we talk about intensities yet? No, I skipped something, sorry. Oh no, there it is. I forgot to do the intensity, sorry. We got this special case, we need to recall what intensity is, sorry. Okay, so if you remember the intensity we computed was 1/2 the speed of light times the permittivity free space times the square of the electric field. And fortunately, this equation up here is in the square. So if we start with this equation and multiply both sides by 1/2 c epsilon naught, we can rewrite it in terms of intensity. Okay, so that's that same equation again. We're just thinking in terms of intensity instead of in terms of electric field strength squared. All right, so now let's return to the double slit and see what we get when we do that sum. So we just have the sum of the intensities plus twice the square root times the phase difference, the cosine of the phase difference. Now in this case, both those intensities are the same, so I1 and I2 are the same as I1. So we could write this as twice I1 plus twice I1 cosine delta phi, which is kind of interesting, so we could factor out that can be similarly written using another trig identity. So now if we put in what the intensity is at that angle, we end up with ran out of room here. And then the cosine squared delta phi over 2. So that's all nice. But we haven't really done the geometry yet. The only thing we've done at this point that's different than what we did before was notice that for the double slit, these two intensities are the same. But again, so far this will work for everything where both of the sources have the same intensity. So now let's look at the geometry of the double slit. So we need to magnify it so that we can actually see it. Now in this picture, the observation screen is very, very far away. so far away that these two lines, even though they converge, appear to be parallel. And I'm going to add a helpful line here. And that's a line that goes from this one down to here, but is perpendicular to that one. Now the reason that's helpful is that if we call this distance R1, that's the distance from this point all the way back to the observation point, then this distance here is also R1, but only right to there. Okay? So you can see that this guy, R2, the full thing, is R1 plus this little piece here, which I'm going to call delta R. Now, we have a triangle. So we got a triangle like this. This is a right angle. That side is D. This is delta R. That's the angle theta. So that tells us that delta R is d sine theta. So the difference in the two R's is d sine theta. Now if we think of the phase over at the observation point, the phase on this one is k times R1. The phase on this one is k times R2. So now we could calculate the difference in the phases. Okay. Now let's go ahead and remind ourselves what the wave number is. Remember, it's 2 pi divided by the wavelength. So we could write it in terms of the wavelength also. Now if you remember what we had up in our equation up here, it was actually a difference in phase divided by 2. So we can continue that. And then we can plug into that equation that we found before. And substitute. Which is actually the equation that we gave before for the intensity of the double slit pattern. It's slightly different because this I used I0 before. This I0 is slightly different. If we go back where it came in, it was here. It's the intensity at the center, right here, with just one slit open. Whereas in the original one, when I wrote out this I0, would have been this whole thing. And that was the intensity of the double slit pattern. So one thing we discover here is that if you take a single slit and measure the intensity, if you open the other slit, you get 4 times as much intensity as you did with just one. That's only at the center. At other places it's darker. So there are some places where it's darker, But there's other places where it's brighter, and it's not just twice as bright. It's up to 4 times as bright as it was with just one of them. Okay. So that was our main goal. We've rediscovered the equation that I gave you from the beginning. Maybe not so great, but the nice thing is that we understand a little better where it came from. Okay, a little bit of trigonometric magic that got from this equation to that equation. And then the geometry, which is not an uncommon geometry, that we found that this very small path difference, I remember this d is a very small distance, so delta r is going to be very small, that we can get that path difference by knowing something that's not small, which is this angle. If we go back up to this diagram, remember that these are like distances you can measure with a ruler, like the distance from the observation screen over to the slit, and the distance from the central maximum out to our observation point. Okay, so I also want you to remember that our phase up here had mins and max when this was n pi. So the maximums were the even pi's and the minimums were the odd pi's. Now we have an expression for this phase difference now in terms of the path difference. Delta r being the path difference, if you remember the difference in the two paths. There were 2 paths to get from the source to the observation point. Delta r is the path difference, the difference in those 2 lengths. Okay, so this is the special cases now. See, we can cancel those off. So we find that if we could write it like this, after a little bit of algebra, so we find that the mins and max of the interference pattern happen when the path difference is a multiple of half a wavelength. If it's an even multiple, then you get a maximum. If it's an odd multiple, it's a minimum.